I'm Bilgin, and today I'm going to share with you how I see distributed systems evolving on Kubernetes. Why me? Because I work for Red Hat, and there I have been a consultant, an architect working with distributed systems using Apache Camel. Apache Camel is a very popular framework in the Java ecosystem for doing integrations. And I'm a committer. I have a book about Apache Camel. And in the latest years, I've used Kubernetes. I also have a book about it. So I've been at the intersection of distributed systems and Kubernetes. First, I want to start with a question. What comes after microservices? I'm sure you all have an answer for that, and I have mine too. And you'll find out at the end what I think that will be. To get there, I suggest we look at what are the needs of the distributed systems and how those needs have been evolving over the years, starting with monolithic applications through Kubernetes and with more recent projects such as Dapr and Istio Knative, how they are changing the way we do distributed systems. And we'll try to do some predictions about the future. To set a little more context on this talk, when I say distributed systems, what I have in mind is systems composed of multiple components, hundreds of those. These components can be stateful, stateless, they can be serverless, components created in different languages, running on different environments, and components created using open source technologies, open standards, interoperable. I'm sure you can create such systems using closed source software. You can create them on AWS and other places, but for this talk specifically, I am looking for the Kubernetes ecosystem and how you can create those on Kubernetes ecosystem. So let's start with the needs of distributed systems. And what I have in mind is, let's say we want to create an application or service. We want to write some kind of business logic. What else do we need from the platform, from our runtime to create a distributed systems? And I would say at the foundation, at the beginning, is we want some kind of lifecycle capabilities. And what I have in mind is, when you write your application in any language, then we want to have ability to package, to deploy that application reliably, to do rollbacks, health checks, be able to place the application on different nodes, and be able to do resource isolation, scaling, configuration management, all of these needs. These are the very first things you would need to create a distributed application. The second pillar, I would say, is around networking. So once we have an application, we want it to be reliably connect to other services, whether these are within the cluster or in the outside world. So we want to have the ability such as service discovery, load balancing. We want to be able to do traffic shifting, whether that's for different release strategies or for some other reasons. And then we want to have a ability to do resilient communication with other systems, whether that is through retries, timeouts, circuit breakers, of course, and have security in place and get good monitoring, tracing, observability, and all that. Once we have networking, I would say the next thing is we want to have ability to talk to different APIs and endpoints, so binding, resource binding, be able to talk different protocols, different data formats, maybe even able to do transform from one data format to another one. I would include here also things such as light filtering. So when we subscribe to a topic, maybe we are interested only from certain events. What do you think is the last category? It is state. So when I say state and stateful abstractions, I'm not talking about the actual management of state, such as what the database does or a file system. I'm talking more about developer abstractions that behind the scene rely on state. So probably you need to have ability to do workflow management. Maybe you want to manage long-running processes. You want to do temporal scheduling, so some kind of cron job to run your service periodically. Maybe you want to do also distributed caching. You want to have idempotency, be able to do rollbacks. All of these are, I would say, developer level primitives, but behind the scene, they rely on having some kind of state. So you want to have these kind of abstractions in your disposal to create good distributed systems. And throughout this talk, we will use these frameworks to evaluate how these needs have been changing on Kubernetes and with other projects. If we start with the monolithic architectures and how we get those capabilities, the very first thing is, when I say monolith, I have in mind, in the context of distributed application, that is the ESBs. So ESBs are quite powerful, and when we check our list of needs, we would say that ESBs had a very good support for all kinds of stateful abstractions. So you could do the orchestration of long running processes, you can do distributed transactions, rollbacks, idempotency. They also have very good resource binding capabilities. So an ESB will have hundreds of connectors, they can do all kinds of transformation, orchestration, and even networking capabilities. So an ESB can do service discovery, it can do load balancing, it has all things around resiliency of the networking connection, so it can do retries, etc. Probably because by nature an ESB is not very distributed, it doesn't need very advanced networking and release capabilities. But where ESB lacks is primarily around lifecycle management. Because it's a single runtime, the first thing is you are limited to using a single language, and that's typically the language that the actual runtime is created in, whether that's like Java or .NET or something else. Then, because it's a single runtime, that means we cannot do easily declarative deployments. We cannot do automatic placement. The deployments are quite big, quite heavy, so usually involve a human interaction. Another difficulty with such a monolithic architecture is around scaling. We cannot scale individual bits. And last but not least, around isolation, whether that's resource isolation, fault isolation. So none of these can be done with the monolithic architectures. And from our needs framework point of view, I would say the ESB's monolithic architectures don't qualify. Next, I suggest we look at cloud native architectures and how those needs have been changing. If you look at how, at very, very high level, how those architectures have been changing, I would say cloud native probably started with the microservices movement. So microservices allow us to split a monolithic application by business domain, and it turned out that containers and Kubernetes are actually a good platform for managing those microservices. Let's see some of the concrete features and capabilities that Kubernetes becomes particularly attractive for microservices. I would say at the very beginning that is the ability to do health probes. So that's something that Kubernetes made popular, and in practice it means when you deploy a container in a pod, Kubernetes will check the health of your process, but typically that process model is not good enough. So you still may have a process that's up and running, but it's not healthy. So that's why there is also the option of using readiness and liveness checks. So Kubernetes will do readiness check to decide when your application is ready to accept traffic during startup. It will do liveness check to continuously check the health of your service. Now, before Kubernetes, this wasn't very popular, but today almost all languages, all frameworks, all runtimes have health checking capabilities where you can easily start an endpoint. The next thing that Kubernetes introduced is around managed lifecycle of your application. What I mean here is you are not any longer in control when your service will start up and when it will shut down. You kind of trust the platform to do that, and Kubernetes can start up your application, it can shut it down, move it around on the different nodes, and for that to work, you have to implement properly the events that the platform is telling you during startup and shutdown. Another thing that kind of, again, Kubernetes made popular is around deployments and having those declaratively. That means you don't have to anymore start a service, check the logs whether it has started. You don't have to manually upgrade instances. Kubernetes with declarative deployments can do that for you. It can, depending on the strategy you chose, it can stop all the instances, start new ones. If something goes wrong, it can roll back, etc. Another thing is around declaring your resource demands. So when you create a service, you containerize it, it is a good practice to tell the platform how much CPU and memory that service will require. And Kubernetes uses that knowledge to find best node for your workloads. Before Kubernetes, we kind of had to manually place an instance to node based on our criteria, but now we can guide Kubernetes with our preferences and it will make the best decision for us. And at the very end, I would say configuration management. Nowadays, on Kubernetes, you can do polyglot configuration management. So you don't need in your application runtime anything to do configuration lookup. Kubernetes will make sure that the configurations end up on the same node where your workload is, and the configurations are mapped as a volume or environment variable ready for your application to use. And it turns out those specific capabilities I just spoke about, they are also related. For example, if you want to do automatic placement, you have to tell Kubernetes what are the resource requirements of your service. Then you have to tell it what deployment strategy to use. In order for the strategy to work properly, your application has to implement the events coming from the environment. It has to implement health checks. But once you put all of these best practices, once you use all of these capabilities, your application becomes a good cloud-native citizen and it's ready for automation on Kubernetes. And in my view, this represents the foundational patterns for running up workloads on Kubernetes. Then there are other patterns such around structuring the containers in a pod, doing configuration management and behavioral. The next topic I want to briefly cover is around workloads. So we said from lifecycle point of view, we want to be able to run different kind of workloads. And we can do that on Kubernetes too. So running 12-factor apps, stateless microservices is pretty easy, and Kubernetes can do that. But that's not the only kind of workload you will have. Probably you will also have stateful workloads, and you can do that on Kubernetes using a stateful set. Another kind of workloads you may have is a singleton. Maybe you want an instance of an app to be there to be only one instance of your app throughout the whole cluster, and you want it to be a reliable singleton. So when it fails, it should be started up. And you can choose between stateful set and replica set, depending on your needs, whether you want the singleton to have at least one or at most one semantics. Another kind of workload you may have is around jobs and cron jobs. So with Kubernetes, you can do those as well. If we map all of these Kubernetes features to our needs we've been talking about, I would say Kubernetes satisfy really well the lifecycle needs we've been talking about. And in fact, the list of needs I created are primarily driven by what Kubernetes provides us today. And these are kind of expected capabilities from any platform. Kubernetes can do for you deployment, placement, configuration management, resource isolation, failure isolation, and it supports different kind of workloads except serverless on its own. Then, if that's all what Kubernetes gives for developers, how do we extend Kubernetes? How can we make it give us more features? So I want to briefly talk about two main ways that are used today. The first thing is the concept of a pod. So pod is an abstraction used to deploy containers on nodes, and the pod gives us two sets of guarantees. The first set is deployment guarantees, so all containers in a pod always end up on the same node. That means they can communicate with each other over localhost or asynchronously using the file system or through some other IPC mechanism. And the other set of guarantees a pod gives us is around lifecycle. Not all containers within a pod are equal. So depending if you are using init containers or application containers, you get different guarantees. For example, init containers are run at the beginning when a pod starts. They are run sequentially, one after another, and they run only if the previous container has completed successfully. So they are good for implementing some kind of workflow logic driven by containers. And application containers, then they run in parallel. They run throughout the life cycle of the pod. And this is where the sidecar pattern comes in. The sidecar is the ability to run multiple containers that cooperate with each other and jointly provide a value to the user. That's one of the primary mechanisms we see nowadays for extending Kubernetes with additional capabilities. In order to explain the next capability, I have to briefly tell you how Kubernetes works internally, and it is based on the reconciliation loop. So the idea of the reconciliation loop is to drive the desired state to the actual state. And within Kubernetes, there are many bits that rely on that. For example, when you say, I want 2 instances of a pod, this is the desired state of your system. And there is a control loop that constantly runs and checks if there are 2 instances of your pod. And if there are not 2 instances, if there is 1 or more than 2, it will calculate the difference and it will make sure that there are 2 instances. So there are many examples of this. Some are like replica set, stateful set. You can see the resource definition maps to what the controller is. So there is a controller for each resource definition, and this controller makes sure that the real world matches the desired one. And you can write your own custom controller. Let's say you have an application that's running in a pod and it cannot load configuration file changes at runtimes. So you can write the custom controller that detects every time a config map changes, it restarts your pod so that your application is restarted and it can pick up configuration changes at startup. That would be an example of a custom controller. Now, it turns out that even though Kubernetes have a good collection of resources, that they are not enough for all the different needs you may have. So Kubernetes introduced the concept of custom resource definitions. That means you can go and model your requirements and define an API that lives within Kubernetes. It lives next to other Kubernetes native resources, and you can write your own controller in any language that understands your model. So you can design something like a config voucher implemented in Java that describes what we described earlier. And that is what operator patterns is. So operator pattern is a controller that works with the custom resource definitions. And today we see lots of operator coming up, and that's the second way for extending Kubernetes with additional capabilities. Next, I want to briefly go over a few platforms that are built on top of Kubernetes, and they are using heavily sidecars and operators to give additional capabilities to developers around distributed systems. And I want to start with the service mesh. So what is a service mesh? Let's say we have 2 services, service A that wants to call service B. It can be in any language. That's basically our application workload. What service mesh does is, using sidecar controllers, a service mesh injects a proxy next to our service. So you end up with 2 containers in the pod, and the proxy is a transparent one. So your application is completely unaware that there is a proxy that is intercepting all incoming and outgoing traffic. And the proxy acts also as a data firewall. The collection of these service proxies represents your data plane. Now, these proxies are small, they are stateless, and in order to get all the state and configuration, they rely on the control plane. The control plane is the stateful part that keeps all the configurations. It gathers metrics, takes decisions, and interacts with the control with the data plane. And you can see there are good choice for different control planes and data planes. it turns out we need one more component. So we need an API gateway in order to get data into our cluster. Some service meshes have their own API gateway and some use third-party, but all of these components, if we look into those, they provide the capabilities we need. An API gateway, it is primarily focused to abstract the implementation of our services, so it hides the details and provides borderline capabilities. Service mesh, it does the opposite. In a way, it enhances the visibility and reliability within the services. But jointly, we can say that API gateway and service mesh provides all the networking needs we've been talking about. So that in order to get networking capabilities on top of Kubernetes, using just the services is not enough. You need some kind of a service mesh. The next project I want to mention is Knative. It's a project started by Google a few years ago, and it's getting very close to GA. It is basically a layer on top of Kubernetes that gives you serverless capabilities, and it has two main modules, serving and eventing. Serving is focused around request-reply interactions, and eventing is more for event-driven interactions. Just to give you a feel what is serving. In serving, you define a service, but that is different than a Kubernetes service. This is a Knative service. And once you define a workload with a service, you basically get something like a deployment, but with the serverless characteristics. So you don't need to have an instance up and running. It can be started from zero when a request arrives. So you get serverless capabilities. It can scale up rapidly. It can scale down to zero, etc. If you look at the eventing, eventing gives us a fully declarative event management system. So let's assume we have some external systems we want to integrate with, some external event producers, and at the bottom we have our application in a container that just have an HTTP endpoint. With Knative Eventing, we can start a broker. We can start a broker that's mapped by, let's say, Kafka, or it can be in memory or some kind of cloud service. We can start importers that connect to the external system and import the events into our broker. And those importers can be, for example, based on Apache Camel, which has hundreds of connectors. Once we have our events going to the broker, then again, declaratively with the YAML file, we can subscribe our container to those events. And in our container, we don't need any kind of messaging client. We don't need the Kafka client, for example. Our container would get the events through HTTP post using cloud events. So as you can see, this is a fully platform managed messaging infrastructure, and you as a developer, all you have to do is write your business code in a container and don't deal with any kind of messaging logic. From our needs point of view, I would say Knative satisfies few of those. So from lifecycle point of view, it gives our workload serverless capabilities, so ability to scale to zero and scale up, activate from zero and go up. From networking point of view, there is some overlap with the service mesh, because Knative can also do things such as traffic shifting. From binding point of view, it has a pretty good support for binding using Knative importers. It can give us pub/sub or point-to-point interaction, or even some kind of sequencing. So it satisfies the needs in a few categories. The next project that is again using sidecars and operators is Dapr. Dapr is started by Microsoft only a few months ago, but rapidly getting popular. And it is basically a distributed systems toolkit as a sidecar. So everything in Dapr is provided as a sidecar. And it has a set of what they call it building blocks, so a set of capabilities. If we look briefly, what are those capabilities? The first set of capabilities are around networking. So Dapr can do service discovery and point-to-point integration between services. Similarly to service mesh, it can also do tracing, it can do reliable communication, so it can do retries, recovery, etc. The second set of capabilities are around resource binding, so it has lots of connectors to cloud APIs, different systems, and it can also do messaging, basically publish, subscribe, and other logic. But interestingly, Dapr also introduces the notion of state management. So in addition to what Knative and Service Mesh gives you, Dapr also have abstraction on top of the state store. So you can have key value-based interaction with Dapr that is backed by the actual storage mechanism. So at a high level, at the architecture is you have your application at the very top, which can be in any language. You can use the client libraries provided by Dapr, but you don't have to. You can just use the language features to do HTTP and gRPC call to the sidecar. Now, the difference to Service Mesh is that here this Dapr sidecar is not a transparent proxy. It is an explicit proxy that from your application you have to call and interact with over HTTP or gRPC. And depending on what capabilities you need, Dapr can talk to other systems such as cloud services. On Kubernetes, Dapr deploys as a sidecar, but Dapr also works outside of Kubernetes, so it's not only Kubernetes. And it also has an operator. We said sidecars and operators are the primary extension mechanism. And there are a few other components to manage certificates, to deal with actor-based modeling, and for injecting the sidecars. But as you can see, your workload, again, interacts with the sidecar, and the sidecar does all the magic to talk to other services, which can give you some kind of interoperability with different cloud providers, and it gives you additional distributed system capabilities. If I were to sum up what these projects are giving you, we can say that ESBs were the early incarnation of distributed systems, where we had centralized control plane, we had a centralized data plane, so it didn't scale really well. With cloud native, we are going towards, there is still centralized control plane, but the data plane is decentralized, it's highly scalable with good isolation. So we always would need Kubernetes to do good lifecycle management. Then on top of that, you would need probably one or more add-ons. You may need Istio to do advanced networking. You may use Knative to do serverless workloads, or Dapr to do integration. And those frameworks play nicely with, say, Istio and Envoy. From Dapr and Knative point of view, probably you have to pick one. But jointly, I would say they are providing what we used to have on an ESB in a cloud-native way. Now, for the next part, I have basically done an opinionated list of a few projects where I think interesting developments are happening in these areas. And I want to start with Lifecycle. So with Kubernetes, you can do actually, as we covered, we can do good lifecycle for your application, but that might not be enough for more complex lifecycle management. For example, you may have scenarios where the deployment primitive in Kubernetes is not enough for your application if you have a more complex stateful application. And in these scenarios, you can use the operator pattern. So you can use an operator that does a deployment and upgrade, where it also backs up maybe the storage of your service to, let's say, S3. Another thing is that you may find out that the actual health checking mechanism in Kubernetes is not good enough. So if liveness check and readiness check is not good enough, you can use an operator to do more intelligent liveness and readiness check of your application, and based on that to do recovery. A third area would be auto-scaling and tuning. So you can have an operator to understand better your application and do auto-tuning on the platform. And today there are, I would say, primarily two frameworks for writing operators. the kube builder from Kubernetes Special Interest Group, and the operator SDK, which is part of operator framework that I'm more familiar with. So operator framework is created by Red Hat, and it has a few things. So there is the operator SDK that lets you write operator. There is operator lifecycle manager, which is about managing the lifecycle of the operator itself, and operator hub, where you can publish your operator. So if you go there today, you will see there are over 100 operators that manage things such as databases, message queues, monitoring tools, etc. And I would say from lifecycle space, probably operators are the area where most active development is happening right now on the Kubernetes ecosystem. The next project I picked is Envoy, and on the networking side, I would say we've seen this morning what's happening with Service Mesh and Istio. So there is the introduction of Service Mesh interfaces specification that will make it easier for you to switch different Service Mesh implementations. There's been some consolidation on Istio architecture in the deployment, so you don't have to deploy 7 pods for the control plane. Now you can just deploy once. But more interestingly is what's happening at the data plane at and the Envoy project. So we see that more and more layer 7 protocols are added to Envoy. So Service Mesh is adding support for more protocols such as MongoDB, Zookeeper, MySQL, Redis, and the most recent one is Kafka. And I see that the Kafka community is now further improving their protocol to make it friendlier for service meshes. So we can expect that there will be even more tight integration, more capabilities. So most likely there will be some kind of bridging capability. So in your service, you can do an HTTP call locally from your application, and the proxy will, behind the scene, can use Kafka. So you can do things such as transformation, encryption outside of your application in a sidecar for the Kafka protocol. Another interesting development has been the introduction of HTTP caching. So now Envoy can do HTTP caching. You don't have to use caching clients within your applications. All of that is done transparently in a sidecar. There are tap filters, so you can tap the traffic and get the copy of the traffic. And most recently, the introduction of WebAssembly. That means if you want to write some kind of custom filter for Envoy, you don't have to write it in C++ and compile the whole Envoy runtime. You can write your filter in WebAssembly and deploy that at runtime. And I would say all of these, most of these are still in progress. They are not there, but these give me an indication that the data plane and service mesh have no intention at stopping just supporting HTTP and gRPC. They are interested in supporting more application layer protocols to offer you more, to enable more use cases. Especially with the introduction of WebAssembly, you can now write your custom logic in the sidecar. And I guess that's fine as long as you are not putting there some business logic. Next project I want to talk about is Apache Camel. That's a project I love. It is a project for doing integrations, so it has lots of connectors, hundreds of connectors to different systems. It is using enterprise integration patterns. But the way it's related to this talk is in the latest version, Camel 3, it is getting deeply integrated into Kubernetes. And it's using the same primitives we spoke so far, such as operators. So in Camel, you can write your integration logic in languages such as Java, JavaScript. Here the example is with using YAML. And in this in latest version, they have introduced a Camel operator. So that's something that runs in Kubernetes that understands your integration. So when you write your Camel application, deploy it to custom resource, the operator then knows how to build the container, how to find dependencies, and depending on the capabilities of the platform, whether that's Kubernetes only, whether that's Kubernetes with Knative, it can decide what services to use and how to materialize your integration. So there is quite a lot of intelligence that is going outside of your runtime but into the operator. And all that happens pretty fast. And why I would say it's a binding trend, mainly because the capabilities of Apache Camel with all the connectors it provides. But the interesting point here is how it integrates deeply with Kubernetes. The next project I picked is Cloud State, and it's around the state-related trends. And Cloud State is a project by, I think it's Lightband, and it is primarily focused for serverless and function-driven development. And again, with their latest releases, they are integrating deeply with Kubernetes, using sidecars and operators. And I think they also have integration with Dapr, Knative, and all of this. And the idea is when you write your function, all you have to do in your function is use gRPC to get state, to interact with state. And the whole state management happens in a sidecar that is clustered with other sidecars, and it enables you to do things such as event sourcing, CQRS, key value lookups, messaging, etc. But from your application point of view, you are not aware of all of these complexities. All you do is a call to a local sidecar. And the sidecar handles the complexity, and it can be used behind the scene to different data sources. So it has all the stateful abstractions you would need as a developer. A project definitely to follow and see what's happening. So we have seen what is the current state of the art in the cloud native ecosystem and some of the recent developments that are still in progress, but how to make sense of all that. If we look at how microservice look like on Kubernetes, I would say you probably need, you will need to use some functionality from the platform. You will need to use Kubernetes features for the lifecycle management primarily. Then most likely transparently your service will use some kind of service mesh, something like an envoy to get enhanced networking capabilities, whether that's a traffic routing, resilience, enhanced security, or even if it is just for a monitoring purpose. On top of that, you will, depending on your use case, you may need something like Dapr or Knative, depending on your workloads. And all of this represents your out-of-process additional capabilities. And what's left to you is to write your business logic not on top, but as a separate runtime. So most likely, future microservices will be this kind of multi-runtime composed of multiple containers. Some of those are transparent, some of those are very explicit that you use. If I look a little bit deeper how that might look like, I would say you write your business logic in some kind of high-level language. It doesn't matter what it is. It doesn't have to be anymore Java only. You can use any other language. You develop your custom logic in-house. Then all the interactions of your business logic with the external world happens through a sidecar. And that sidecar does, it integrates with the platform, does the lifecycle management, it does the networking abstractions for external systems, gives you advanced binding capabilities and state abstraction. But the sidecar is something you don't develop. You get it off the shelf, you configure it with a little bit of a YAML or JSON, and you use it. And that means you can update sidecars easily because it's not anymore embedded into your runtime. So it makes patching, updating easier, and it enables polyglot runtime for our business logic. And that brings me back to the original question I've asked at the beginning, what comes after microservices? So if we see how the architectures have been evolving, application architectures at a very high level. Yeah, this is a simplification, but hopefully you get the idea. We started with monolithic applications, and microservices allow us to, it gives us the guiding principles on how to split a monolithic application into separate business domains. And after that came serverless and function as a service, where we said, okay, we can split those further by operation, and this gives us ability for extreme scaling, because we can scale each operation individually. But I would argue that maybe fast is not the best model, and functions are not the best model for implementing reasonably complex services where you want multiple operations to reside together when they have to interact with the same data set. So probably something like multi-runtime, I call it MEC architecture, where you have your business logic in one container, and you have all the infrastructure-related concerns as a separate container, and they jointly represent a multi-runtime microservice. Maybe that's a more suitable model because it has better properties. You get all the benefits of microservice, so you still have all your domain, all the bounded context in one place, and you have all the infrastructure and distributed application needs we talk about in a separate container, and you combine them at runtime. Probably the closest thing that's getting to that right now is Dapr. I would say they're following that model. And if you're only interested from networking aspect, probably using Envoy is also getting close to this model. Last part, check out my book. On this link, you can get a free copy at the moment. And yeah, follow me on Twitter. Thank you.